Do it again.
If it's 100% aluminum, how many grams did you get?
0.0173, or what's that for?
0.0173.
Well, it's 373 at the end.
373?
373, yeah.
Okay, 0.01373.
No, 0.017,
0.017?
373.
373, thanks. Grams of hydrogen.
0.01.
Could this sample be 100% aluminum?
That's what I get.
No, it's not possible because how much hydrogen did we generate?
More than what?
0.016. This is 0.017. And so if it were aluminum, we should 100% aluminum, we should have generated a little bit more hydrogen. And so it can't be 100% aluminum. Did everybody get this? Or was able? Or is anybody getting stuck with this? Yeah, how many sig figs are we allowed? We're only allowed 3 sig figs, but you know we carry extra here, so it's 0.0173 sub 7.3 or sub 7. We're only allowed 3 sig figs. But did a stoichiometry problem like this is okay? It's okay. All right. So that's not, step 1's not a hard stoichiometry problem once you've done a bunch of them. And then what's step 2?
Assume 100%.
Yeah, we go to the opposite extreme. We assume 100% magnesium and then just do a stoichiometry problem, right? Did you guys get the hydrogen?
Yeah. 0.01.
0.012.
8. Do we stop at 9?
8. Give me one more.
5.
5. We stop here. We don't round that, but we usually go one more to prevent round off error. Sometimes in these problems, the difference is very small. Like the difference, if it's 100% one extreme versus 100% the other extreme, the difference is so small that you have to carry a lot of extra digits in order to determine, because if you round it, it looks like it's both. And so, you know, this doesn't always work well. The difference has to be significant and measurable for this method to work. All right, then go ahead and graph it. How are you going to graph it? What would you use for your x-axis? Would you use 0 to 100 aluminum or 0 to 100 magnesium for your x-axis? Well, it depends if you want a negative slope or a positive slope. Yeah. If you want a positive slope, you go 0 to 100 aluminum. If you want a negative slope, you go 0 to 100% magnesium. What time do we go till?
55.
55? Okay. And so, does everybody see that? We want to go from 0% to 100% aluminum because we want the bigger number up here. And the bigger number is going to be 0.017373. This is grams of hydrogen. And then the smaller number here, 0.01285. Again, we're only allowed 3 sig figs, so I can go like that. Then we assume that this relationship is linear, which is a good assumption. And then we get the equation for this line, and then solve for percent aluminum. This is what for 2 component mixtures. Is this good? You're okay with this? Yeah, 0.01. I wrote it here. 0.0163.
Yeah, 1, 2, 8,
All right, let's look at 117. 117 is this mixture, copper 2 chloride and iron 3 chloride. And we have 0.7391 grams of this mixture.
Should we put on that?
But this mixture is going to produce different amounts of silver chloride. This is a different kind of reaction. What type of reaction is this? It's not a single replacement. Do you know what this is called?
Double?
This is a double replacement reaction. In fact, we're going to get precipitation. So this is precipitation reactions. And so what they do is there are a couple of additional complications here. And that is, one, if it takes 86.91 milliliters of 0.1463 molar silver nitrate to precipitate all the chloride as silver chloride, then what is the percentage by mass of copper in the mixture? And so in this case, what they're doing is they're measuring how much reactant it takes. It's going to take, you know, if we have more iron in there, let's say per mole, then it looks like we need more silver nitrate. We got to look at the mass differences though too. Or vice versa. So it's going to take different amounts of silver nitrate depending on what it is. And so we have this. So we do the same thing. We assume what?
100%.
100%, let's say copper, and then figure out, you know, if it's 100% copper, we would figure out how many grams of CuCl2 we generate, right? And so this is working backwards versus this. If it's 100% iron, we figure out, you know, we get the from the volume and the molarity, we get the moles of silver nitrate. From the moles of silver nitrate, we get the moles of iron 3 chloride. From the moles of iron 3 chloride, we get the grams of iron 3 chloride. And then we can compare it to the mixture here. And we can see, you know, if it's 100% iron, we get this many grams of mixture, whatever, and then compare it to that. If it's 100% copper, we get, you know, we go from volume to moles, moles to moles, moles to grams, and then figure out. And so in this case, we're comparing the grams of mixture with the grams of pure, you know, if it was pure this and pure that. Does that make sense? So it's the same kind of technique here. Now, the other type of mixture you're going to encounter in chapter 4 is this here. The other type of mixture you'll encounter is one in which there's only one reactive component. And so chalkboard chalk is made from calcium carbonate, calcium sulfate, and some minor impurities such as quartz. So only the calcium carbonate reacts with HCl. The calcium sulfate will not, and the SiO2 will not. And so there's only one reactive component in this mixture. And so the calcium carbonate reacts with HCl. They're asking what is the mass percent of calcium carbonate in a piece of chalk if a 3.28 gram sample yields 0.981 grams of CO2. And so we know that this 0.981 grams of CO2 all came from the calcium carbonate. And so what we can do is go from grams of CO2 to moles of CO2, moles of CO2 to moles of calcium carbonate, moles of calcium carbonate to grams. Now the number of grams of calcium carbonate will be less than 3.28. And so let's say it's half. If it's half of 3.28, then it's 50% by mass, right? And so whatever grams we can get here, we can figure out the percent by mass. And so that's the other type of mixture that we might encounter. That's a mixture on the product side. We get mixtures on the on the reactant side. We get mixtures on the product side as well. The mixtures on the product side can complicate things. And so in this chapter, we're going to see a series of reactions like this. The following set of reactions is to be used as the basis of the method for producing nitric acid. You know, calculate the minimum masses of nitrogen, hydrogen, and oxygen required per kilogram of HNO3. And so when we look at this, it looks like we got a very complicated mixture of things going on here. But in reality, this is something we do. This is what we call a sequence of reactions here. And a sequence of reactions is not that complicated, because what happens is, all this nitrogen and hydrogen produce ammonia, and all that ammonia is consumed in this next step, et cetera. And so this is what we call consecutive reactions or simultaneous reactions. Sometimes we have simultaneous reactions like this. This would be an example of simultaneous reactions. In fact, all we've been doing are simultaneous reactions. Aluminum reacts simultaneously with magnesium, right? Iron reacts simultaneously with the copper. And so these are simultaneous reactions. So let's take a look at this one. How many grams of HCl are consumed in the reaction? 425 gram mixture containing 35.2% magnesium carbonate and 64.8% magnesium hydroxide by mass. And so they want to figure out how much HCl. Well, both of these require HCl, so they want the total amount of HCl that's going to be consumed. And so in this problem, this is the easier version of what we just did. What we just did was problem number 83 backwards. This is these problems forward. If we already knew how many grams of aluminum and how many grams of magnesium we have, then it's just a simple stoichiometry problem. If we know how many grams of aluminum, we figure out how many grams of hydrogen generated. We know how many grams of magnesium, we figure out how many grams of hydrogen are generated, and just add those two up, right? Well, in this case we do, because if we have 425 total grams, then we can figure out 35.2 out of 100 of the 425 grams will be magnesium carbonate, so we can figure out how many grams of magnesium carbonate we have. So in this type of problem, we go from grams of mixture to grams of magnesium carbonate, from grams of magnesium carbonate to moles of magnesium carbonate, moles of magnesium carbonate to moles of HCl. And then the same thing, we go from grams of mixture to grams of magnesium hydroxide, because for every 100 grams of mixture, we have 64.8 grams of magnesium hydroxide. And for every 100 grams of mixture, we have 5.2 grams of magnesium carbonate, because these are percentages by mass. Does that make sense? Yeah or no? Not really. And so in this case, the number 83 is just the ones we just did, but a lot easier because we don't have two equations, two unknowns. We just do these as two separate stoichiometry problems and then add it up. Does that make sense there? And so number 83 is the start, and then you look at the other ones we just did, and it gives you an idea how it works. And so those are some mixtures. We started off complicated in chapter 4 because we're dealing with mixtures, but we ended chapter 3 complicated because we're dealing with a stoichiometric mixture. And so then we're going to look at some of the easier topics in chapter 4 next time we meet.